Okay, so we'll move on to our speaker tonight. Tonight we have Dr. Andrea Rajšić, who is a Lunascope postdoc at Brown University. So for those unfamiliar with the Lunascope program, it's a program that's funded by NASA to conduct scientific research to facilitate our return to the moon. So it's part of that whole Artemis project. And Brown University was one of five institutions that were chosen to have these groups chosen to collaborate on lunar science. So tonight, she will give us a talk on impact cratering. So please welcome Dr. Andrea Rajšić.
Hey everybody. So my name is Andrea, and as Michael said, I'm a postdoc at Brown University. Oh, can you hear me? No.
Yeah, bring it a little closer to you. Yeah.
Okay, I'll hold it. So as Michael said, I'm a postdoc at Brown University. My main expertise is in the impact physics of impact craters. So I study how impact craters form on different bodies. Right now I'm focusing on the moon. And so today I hope to show you that we can resolve whole lunar history by understanding how impact craters form. So before we start talking about impact physics, this is the moon. And Galileo in the 17th century detected all these circles on it. And he said that those are impact craters. However, until 1930s, most astronomers believed that these craters were extinct volcanoes. And some of geologists, even up until Apollo era, so until 70s, were convinced that these circles are just volcanic calderas. So why is that? First of all, today we have 194 confirmed impact craters on planet Earth. And so they're all around, a lot of them in Australia, where I did my PhD, but like they're all around continents. So when we look at the moon, there's way more. And in the past, especially like in the past when we had more observations from the Earth than from the moon, from the nature of like geology, people were comparing structures to each other. And so because we didn't have a lot of impact craters on Earth confirmed, they were just like, why would we have thousands of craters on the moon when we only have 100-ish on Earth? So it was easy for geologists at the time and astronomers at the time to believe that these were volcanoes. Another argument against impact cratering was that impact craters on the moon are visible by eye. So there must have been, scientists believe that there must have been very big bodies that hit the moon and that made those craters. Later on, in preparing for Apollo missions, we did a lot of impact experiments in laboratories like this one. And we learned that a small body impacting at very high speed, so here 2 kilometers per second, can make a crater that is 10 times bigger than the impacting body. So this was another argument from impact physics that showed that we don't need to have a big meteorite or asteroid hitting the moon in order to create craters that are visible by human eye. That's another argument for impact physics. Yeah. So very small body can create a very big crater. And if you look at the kinetic energy, so velocity squared, velocity controls how big the shock wave will be that excavates the crater cavity. And finally, this is a complicated plot, but if we go back and look at the moon, these craters are circular. And so from orbital dynamics, we know that the most common impact angle, so the angle at which body will hit the surface of the moon, is 45 degrees. Why are then craters circular? We would expect them to be oblique. And then again, impact experiments in the 70s showed that up until angle of almost 15 degrees, from the surface, we can form a circular crater. So this is the diameter ratio, basically measuring diameter of the crater perpendicular in the line of impact and perpendicular to the impact. And if it's 1, that means that the crater is circular. So crater is circular from vertical and then all the way to around 15 degrees. So this was third argument from impact experiments that showed that we can get visible big craters that are circular on the lunar surface. And now, how does crater look like? So here we have crater, simple crater, something that we imagine that we will see generally from meteorite impacting the lunar surface, right? So a bowl-shaped feature, very raised rims, bowl-shaped interior, and ejecta around them. However, as we get larger in size, and on the moon, this is craters larger than 20 kilometers in diameter, we get more complex structures. So this is Tycho that John talked about earlier, which has diameter of around 85 kilometers, so from here to Boston. And this crater is, if you compare it to this one, first of all, it has much shallower rim. It's not that pronounced, but then it's very terraced coming into the interior, and then it's flat floored. So it's not like a bowl. And then it has this very big peak. We call it central peak. So it basically has a mountain in the middle. And then if we grow even larger in size, this peak basically becomes wider and forms a ring. So we still have these terraced walls, but the ring gets much wider. And this happens on the moon, and the diameter is larger than 200 kilometers. So 2 times the distance to Boston. So basically, these are the 3 main morphological differences between impact craters on the moon. And each one of these can tell us a different story about lunar history. I will skip this. But yeah. So what I study is the difference between these 2. When we look at this crater, it looks very similar to when we drop a rock into the water, right? But the main difference between these 2 pictures is that rocks have strength. So rocks are solid, whereas this is liquid. So why do we then get this central peak? And why do we get these terrace streams? So, and this is the big question of my research. Why do rocks become like fluids when hit by meteorite? This is now how I study stuff. I do mainly numerical modeling, and this is, imagine this is a surface of the moon. So this is depth, and this is radial distance, and this is a meteorite impacting a surface. Left from the origin, so left from the place where the impact happens, I'll show pressure that is generated by impact. And on the right-hand side, I will show vibrational velocity. What is that? Imagine meteorite hitting the surface. Not only that it opens a crater, forms a crater, it also shakes. So there will be a lot of quakes generated by this impact. And so this is exactly that. So we get a pressure wave that is very strong, and it actually excavates the cavity because it goes further, it opens the cavity, and behind this shock wave, we get these vibrations. And these vibrations, as the pressure wave progresses, they start shaking the ground. And we call this vibrational field. Now, if we look at why these vibrations are important, is because if we measure them, this is lithostatic pressure. And this is how our particles oscillate around lithostatic pressure. As they oscillate, whenever rock strength drops below lithostatic pressure, we will get sliding. We will get uplift of that central peak. How we can imagine that is basically imagining the toothpaste. We have Newtonian liquids and Bingham plastic liquid. Newtonian liquids will flow whenever there is any kind of stress. If you pour water, as soon as you pour it, it will flow, right? But in being on plastic liquids, you need to apply certain yield stress for a liquid to start flowing. And that is the best example for that is toothpaste, right? So it's in the tube, and it's gonna stay in the tube even if you open it and you turn it upside down, it'll be in it. But when you press the tube, it'll start flowing. And that's exactly what is happening to the rocks. And now something is not working. Okay, yeah. So, but what are these vibrations? Vibrations are basically waves in physics, right? Similar to, for example, sunlight. This is a sunset in Newport. We get these beautiful colors in the sky. Why do we get these colors? Because clouds scatter the waves. They scatter the sunlight. And this is exactly what is happening with our waves. They scatter. If we look at the water drop dropping into the water, if we look distant from the place of the impact, these wavelengths become longer and longer in time and in distance. And finally, if we look at AI-generated impact, we get a lot of cracks forming, right? When the impact happens. These cracks, as the crater grows, there will be some movement along them. And so if we look at the actual equation, which I'm not going to bother you too much with, we actually have that scattering term. So scattering of vibrations, we have their decay with time, and we have regeneration of vibrations over time. And this is how energy of vibrations evolves. Now, why is that important? Because as I mentioned in the beginning, I can study craters that are 2,500 kilometers in size, like SPA here at the South Pole, where we're going to land with Artemis. I can study craters that are 90 kilometers in size, like Tycho. And I can study the smallest craters, like all these blue dots, which are craters that are only a few meters in size and form right now as we speak on the moon, by understanding how this vibrational field evolves with time. And so first thing that I'm going to talk about is how can we use this understanding of crater collapse to study how rocks on the moon fracture and generate porosity. And the reason why that is important is because in these fractures we can find water. Now, this is an example of Tycho forming numerical model from 10 years ago. And you can see very nice impact, and then the floor uplifts because we have these vibrations that fluidize the rock, and rock now behaves like a fluid, and we get the uplift. But if you compare it to this picture, besides forming the uplift and the exact size of the crater, what we don't get are these folds, right? This rim here, crater rim, is pretty flat. We don't get these terraces. And this is because, if you remember the equation from the beginning where I talked about scattering and decay and regeneration, initially 10 years ago, these numerical models did not include scattering and regeneration of vibrations. Vibrations only decayed with time and distance, which led to attenuation. So when you have an impact, these vibrations will attenuate in certain distance, right? And that led to a very high coefficient of 30,000 that we measured during Apollo, and it's not that high. How we can imagine this? So from that equation, decay time of vibrations is proportional to Q. Q is basically a quality factor that describes how quickly we lose energy over time. And it is directly proportional to decay time, but it is inversely proportional to attenuation. The easiest way to imagine this is to imagine you're entering a completely empty room. and you say something, and you'll get the echo. You get the echo because in an empty room, there is nothing to attenuate the sound. So in empty room, when you speak, you get the echo. Attenuation is very small, but the Q is very large. If you then fill up your room with a lot of stuff, and you again say something, you will not get that echo because all this stuff will absorb the sound. And attenuation in this room will be very small, but the Q will be very high. So high attenuation equals to much lower Q and decay time of vibrations. Vibration like sound or vibration like impact vibration, because vibrations are same. So how does that relate to, for example, Earth? On Earth, we have regions that are tectonically active and regions that are not tectonically active. So this would be some subduction zone and this would be some continental interior. In tectonically active zones, we will have very high attenuation. So similar to our field room with stuff, because we, in tectonically active zone, we have a lot of fractures, we have a lot of heat, we have a lot of volcanism, we have stuff going on. And in this region, vibrations will attenuate very quickly and Q will be much lower. In stable continental interiors, we don't have much going on. It's stable. There are no earthquakes, there is no volcanism, there is nothing going on. We will have very low attenuation, hence very high Q. Why is that important? Because we also have all that stuff measured on the moon from Apollo missions. The moon does not have tectonic activity. For a long time, people thought that moon is empty inside, but it's not, because the waves attenuate much slower on the moon because Q is much higher. But we measured this. And so what I did in my simulations is, if you remember now the simulation from the beginning, sorry about that, but as a reminder, we had impact and then uplift of the floor, but not forming the terrace rims of the crater. If we now look at the simulations that include measured Qs from Apollo seismic networks, this is how non-simulations look like. So my Qs increase from surface to the bottom. We still get the nice, very nice uplift of the crater. And here we get formation of the first folds that resonate the fractures around the Tycho crater. Why is this important? Because, okay, this is more, because in the future, we can actually take the formation of folds around impact craters and take them to, for example, Mars, where understanding how these folds form on the moon, where we don't have any other geological processes, taking this on Mars, where we actually have some activity from atmosphere and all the other geological processes happening there, we can actually predict where hydrothermal activity can occur, and so where we can find them. Going further is, then I studied craters that are much larger, so SPA. All this blue is actually basin, impact basin on the south pole of the moon. And so during rail, we measured the crustal thickness of SPA basin and how it changes from the center of the basin going outward. And if you look at it, it's very gradual. So we have very thin crust, and then as we're going out, it gradually thickens. This crater, this basin here, is called Oriental, and Oriental has multiple rings, whereas SPA has no rings. So when we compare crustal thickness of Oriental to the SPA, we get this strong, rapid increase in crustal thickness, and then going outward, gradual decrease of crustal thickness. And so one of the major things here is that megabasins such as SPA, which is 2,500 kilometers in diameter, is different from multi-ring basins, not only because it doesn't have rings, but also in crustal structure. Now, why is this? Yeah.
How is crustal thickness measured? Is that just a matter of elevation, or is there?
From gravity. Yeah. And also elevation. Yeah. And so why is this important? Why is it important to understand the difference between multi-ring basins and megabasins on the moon? Because these two form the different times of lunar history. SPA is 2,500 kilometers in size. This impact happened over 4 billion years ago. Oriental, which has rings and has this thick crust here, formed around 3.6 billion years ago. It's the youngest impact basin on the moon. What would control the size of this impact is how warm the moon was at the time. And so in the past, numerical modelers were trying to simulate in simulations formation of these basins. And the only way they could get the crustal signature similar, so this thick solid line is what we measured on the moon. And these dashed lines are results from simulations. And so the only way they could match, still like get close to this crustal signature was if they increased, so that this red line, if they increased thermal gradient on the moon to 50 Kelvin per kilometer. So make the moon very hot. Today, thermal gradient on the moon, I think, is around 7 Kelvin per kilometer. So this is many times larger. So they had to make the moon very hot. Now, I talked about my vibrations. In the past, this model just did not include that scattering and did not include that regeneration of vibrations. All the vibrations evolved with time as exponential functions. So as the crater grows, everything would just decay. In my model, because I include scattering and regeneration of vibrations, only at the beginning we get that exponential decay, and then we get regeneration of vibrations over time. Now, this time scale is in seconds, but to form something that is 2,500 kilometers in size, it takes many minutes. So in order to form SPA size impact, it takes 3 hours for the moon to settle down to form the actual crater. And so these are now some of the results from my simulations. 10 minutes after impact, this is the cavity that we formed. This is that there, and radial distance. And these are the vibrations. So they start localizing around the impact. And they still form in the crust of the impact as the uplift. So this is all the mantle that gets up in the air. And now we're into the simulation, we still have some bouncing back of mantle into the air, and vibrations are still present in the target. And 3 hours into the impact, there are still some vibrations happening. Why is that important? Well, I'm not gonna, okay. If we look at that old simulations, this is how long the vibrations lasted in old simulations, and this is what is happening in mine. So we still have vibrations present. And so why is that important? Is because now we can measure crustal thickness from these new simulations. Compared to the SPA, if I include 30 Kelvin per kilometer, my crater has much thinner crust at the center, but still at this part, we don't get that much of the uplift like we get in younger basins like Oriental. At 40 Kelvin per kilometer, my profile basically matches the crustal thickness of observed. And if I increase it to 50 Kelvin per kilometer, which was recommended in the past, my crustal profile is much thinner than what we observe on the moon. So basically what that means is that now with understanding the physics of how vibrations behave during impact cratering, we can actually may understand thermal history at the time of SPA formation, so 4 billion years ago, of the moon much better. But we have large basins like SPA on other bodies, such as Mercury, with or on Mars we have borealis, so much the whole northern hemisphere of Mars is basically a impact basin, and we have these several thousand kilometer big basins on Callisto, which is icy satellite of Jupiter. So people modeled all these basins in the past, and they had to make these bodies very warm. So now that we can actually reduce thermal gradient, we can understand the impact in history and the thermal evolution of all these bodies much better. So what I talked about is how we can reproduce faults on the Tycho and how we can make thermal gradient at the time of SPA formation much better with new models, which then has implications across the whole solar system. And finally, what I will talk about, what I promised, are these small craters that happen as we speak on the moon. So simple craters are all craters that are smaller than 15 kilometers. What I'm going to talk about are craters that are 20 to 100 meters in size, so much smaller. Why are these craters important? Like, okay, basins are important because they happen in a long past of the moon and they can tell us about thermal history of the moon. Complex craters are important because that's where we expect hydrothermal activity to occur. But small craters form in the topmost surface, in the surface where astronauts walk, on the surface where rovers land, on the surface when we go to the moon, we collect samples. So, and this surface is called regolith. Regolith is basically unconsolidated rock, everything that's fractured. Because we have so many impacts on the moon, everything is constantly just gardened by these impacts. They hit the moon, excavate the rock, then another impact happens, excavates the rock, and we get regolith forming. Because we don't have atmosphere or any other geological processes on the moon, the only process that produces regolith is impact cratering, which means that regolith not only is important because we land there, but also because it records the entire history of the moon. And my goal is to understand the thickness of regolith. Understanding the thickness of regolith is important because with going back to the moon, we want to find volatiles. These volatiles will be stored in regolith. How much of those volatiles we can actually extract will depend on how thick that regolith is. In order to estimate the regolith thickness, now I don't model this, we actually map craters. And so here are several examples of how differently these bowl-shaped craters can look like. This yellowish part is basically solid rock. Everything that is white is regolith. So in a situation where crater impacts just the regolith, it will be perfectly bowl-shaped crater. But if this crater actually excavates the rock beneath the regolith, so the solid rock, like you're digging in your garden and you hit the rock, this is what's going to form. We will get rocks inside the crater and outside of the crater. We will get in the images where we map, we will see rocks around the crater. Another example of what can happen is that we can get this concentric crater. So basically, inside of the crater, we can get another little terrace crater because the rock excavated a stronger substrate. And so what I do is I map these non-rocky ejected craters and rocky ejected craters. And so, well, I don't map them, my undergraduate student maps them. And so here, these red dots are Apollo landing sites, and these are Chang'e landing sites, so China missions. Yellow dots are all the areas that we mapped in the Mare, so in the darker regions, and blue dots are all the localities where we mapped craters in highlands. So these are not craters, these are areas. They are much bigger. There's way more craters than we mapped in each of those. And so Mare and highlands are two distinct regions on the moon, right? They form the. Did I send this up?
Like,
Can you hear me?
isn't that the battery somewhere? Maybe the battery.
Wait, the outcome?
We got.
There we go.
Oh, okay.
Another battery.
Okay, cool. So Mare and highlands are two distinct, geologically distinct areas of the moon. Mare is darker when you look at the moon, highlands is brighter. The major difference between these is the age. Mare areas are formed by volcanism that started around 3.8 billion years ago on the moon. All these brighter areas are originally from when lunar crust first formed. So these are intact areas, the oldest areas of the moon that are older than 4 billion years ago. So our goal is to see if these areas will have thicker regolith than these areas in Mars. And so,
Yep. Do you have another battery?
No, I know who they are.
okay. Hello.
Dr. Andrea, you have Apollo 13 there. Are you surveying from the top? Or is that from the ground? I mean, 13 didn't land, of
Or
course.
16.
Oh,
That's
yeah, that's
16?
16, sorry, that's
Battery in the
16,
toolbox.
that's
Toolbox.
16,
Toolbox is battery there.
anyway.
Okay, I made mistakes too. Oh, come on.
Microphone, right?
Yeah, but that's a good
This
catch.
tone just not like somebody. Can
Can you hear me now? Okay. So in this, word,
See if I can keep
Okay.
it very straight. Oh, batteries.
well, while we wait, are there any questions for this part?
So that technical crater is approximately, what, 100 million years old? That the estimate? That's relatively young.
It is, yeah. Yeah, and it's 90 kilometers in diameter, which is pretty big for such a young crater, yeah.
It was accepted that all of the craters on the moon were from impacts. Had anybody made any attempt at modeling what they thought it looked like?
Oh, yes, they had all those different types of volcanism observed on Earth, like forming of the lapillis and forming of the domes beneath the ground and like uplifting. So it was mainly observational. Basically, people were going around the Earth and trying to find something similar to, rather than modeling the volcanism. But yeah, so as a reminder, what we map are craters that have no rocks and craters that have rocks in the ejecta. And the areas where we mapped are some are in Mare and some are in highlands. And this plot shows when we now, from all our mapped craters, we estimate their excavation depth, so how deep they excavated. And these are a number of craters that we mapped. Everything that was mapped in highlands is in orange, in Mare is in orange and in blue. So if we look at the orange line, it stops occurring around 5 meters. So that means that all non-rocky ejecta stop occurring in our data set after 5 meters. Everything after that is just these blue craters. And then in highlands, the purple line stops appearing after 7.5.
It looks like we have a question online. Laura, go ahead.
Yeah, you had a pause for questions earlier, so my question is, you're doing it at different elevations, different types of terrain, but does the type of rock make any difference? Because there are different types of rocks on the moon, and they might have different viscosities that would affect the fluid-like behavior.
Oh, is that for the mapping of regolith or for the larger craters?
Let's just, you said, well, I'm worried, concerned about differences in the chemical composition of the rock.
Okay, yes, so in smaller craters like these, type of rock is very important because these rocks are very sensitive, these craters are very sensitive to where they impact. That's, for example, why we have concentric craters or bowl-shaped craters or rock-ejected craters, because they're sensitive to, are we impacting something that is unconsolidated or consolidated? And this is exactly what with mapping in Mare and highlands we want to see. Not only that these are different in age, but these are different types of rocks.
Yeah,
All these older craters that I talked about are much larger, so they're larger than 20 kilometers in size. At that point, the only thing that controls the cratering mechanics is the speed of the impact and the thermal state of the moon at the time.
okay,
So those larger craters, type of rock does not affect cratering product that much.
thank you.
And so basically what we see here is that in Mare, we start excavating rocks beyond 5 meter depth. And in highlands, we start excavating rocks beyond 7.5 meter depth. And that means that in highlands, we had 2.5 meters thicker regolith than in the Mare region. And we look at how regolith thickness changes with age, because we can measure the surface age of all these places where we measure regolith thickness, and how does that correspond to the decline of impact cratering rate with time. We can see that basically regolith thickness sharply declines around 3.8 billion years ago, and then is roughly constant, which is similar to decline of this black line, which is the decline of impact cratering flux. Another important point at 3.8 billion years ago is the onset of Mare volcanism. So not only that we have declining impact cratering rate, but we have onset of new geological process that basically keeps regolith thickness roughly around 4 to 5 meters. And everything that is older on the surface of the moon has regolith thickness that is much higher than that. And finally, the most important thing is that we used all these measurements and compiled the first map of regolith thickness on the moon. And so if we look at the near side at Apollo 16, we have very, not Apollo 13, we have very thick regolith of 12 meters. Oops. But if we place these green areas over the near side, which are the Mare volcanism, so everything that has Mare units over it, this area is in highlands. So if we compare this with this, all the thin regolith is in the Mare regions, whereas much thicker regolith is around Mare. Why is this important? Is because on the south pole of the moon, we have the oldest rocks. That's why we are going there. Not only for volatiles, but because we want to sample the oldest rocks from the moon. Can we sample them if regolith is 10 meters thick? That's the question. But finally, to wrap up, we can use craters to understand how basins form in the earliest times of the moon, and to understand how warm the moon was at the time of this basin formation. Smaller craters like Tycho, we can use in order to understand how rocks fracture and how we induce porosity in them, in order to understand cratering on other planets, and to understand where we can expect hydrothermal activity. And finally, we can understand regolith production. So how much regolith we will have on the surface of the moon, and how much volatiles we can extract from them. So we can use craters to understand everything on the moon. Yeah. That's it.
Any questions for Dr. Rajšić?
I have a question.
Mhm.
So in your research or in the sort of the broader field, what has impact craters revealed about the history of planetary surfaces or evolution that may have surprised you the most?
Well, a lot. Well, first of all, the fact that how we can understand the thermal evolution of the planet, because we cannot model. I think every time we model a crater, people expect that we just put things in the code and we get the crater, but we need to understand the history of the moon. And if we don't understand the history of the moon well, the products of the model will not be well. So then it's kind of like informing each other. On the other hand, I think for me right now, it's very interesting to understand the fracturing, because we have observed hydrothermal activity on craters on Earth. So we have collections of rocks, we have like, we know that it's happening. So understanding how that happens is very good.
Thank you.
Oh,
I have a question online.
Go ahead, Craig. Go ahead, Greg.
Okay. Can you hear me all right? All right, great. I have a question. How would you create a crater in a metal asteroid? The Psyche mission is currently heading to asteroid Psyche, which is a metal asteroid. And I've seen, modeling from it from radar, and there's like one huge crater. I can't even imagine, how would a rock create an impact on a metal? It must be metal impacting metal. Can you comment on that, please?
yeah. So that's whole another big field, and it is very interesting. And yes, impacts on metal worlds are definitely way different than what we observe on rocky worlds or icy worlds.
Yeah.
It does not necessarily have to be a metal on metal if the body is very fast. So that's this slide that I probably didn't take enough time on. But if we look at the experiment, so we have a very small body impacted at very high speed. So if on Psyche velocities are probably over 30 kilometers per second, you can imagine that a small rock impacting at that speed will create a crater on a metal world.
Oh, wow. Okay. I wasn't aware of that. Thank you. So the velocity makes a big difference. Okay.
Dr. Andrea, last night I was observing an area of the moon, Salinas Valley, which is actually a string of craters. And on the moon, as you know, there are many long linear strings of craters. Is that the result of a very oblique angle coming in? And is that a swarm of material, or is that like ejecta from the first impact skipping?
Yes, it can be both.
Okay.
So, but it's probably the ejecta. So if we, for example, impacted a strong rock and excavated all these little rocks here, these little rocks, if they fly far enough, they will make secondary craters. So they will make secondary little craters, baby craters, that we can then see from the larger rock.
But why are a lot of them circular and not oblique? Because, you know, if it's coming in at an angle and then this ejector is going forward, it's not like a direct impact. I mean,
Yes, but they also have a high velocity. The ejecta has its own high velocity, yeah.
Messier A and B are elliptical, aren't they? Kind of oblique. Messier A and B craters.
Yeah,
Those are two separate impacts.
yeah,
They're not the
so
same.
they must have been very shallow. So if the crater is circular, then it's like if the parent crater is circular, then the angle of impact was probably not like below 15 degrees, so it was much higher. So all these secondary craters that you see is probably from ejecta. But then if the crater is oblique, then the impact angle is probably not shallow.
didn't you say at some point that a lot of the craters have impact angles of 45 degrees or so?
Yeah.
Got where I was going with this.
Yeah,
With the shape of the
Okay,
crater.
very correctly interested.
Yeah.
But also, most ejected does get launched at a pretty high angle, so then it comes back down.
yeah.
Also, so it's not really
For example,
being launched sideways, it's more being launched up and then falling back down.
yeah, if you look at the movie, for example. So it's very, very. I mean, this is all. Well, takes time, sorry. Yeah, but it's,
Straight up.
yeah, straight up.
Or 0 degrees.
So those coming up, that ejecta could be impacting, making little craters and making those lines.
Yeah, so what we don't see in this as well, and what we see better in my simulation here, is all the vapor that is created.
Yeah, so all that debris can
Yeah.
scatter and make other.
So not only that we have forming of the ejecta blanket, but we also have forming of the vapor cloud that goes up. And it also can contain rocks, like solid rocks. Yeah, that are ejected at much higher speeds than ejecta blanket.
But the lines of craters are gonna be longer if the angle is more oblique coming in, right?
Yes.
Okay.
Yeah, and longer on one side, great.
Okay.
Yeah, so that is correct, like. Even if we have 45-degree impact angle and the crater is circular, that does not mean that ejecta will be circular. The angle of impact is much, how we usually estimate it is by measuring the ellipticity of the ejecta blanket around the crater. Because craters will be circular, but ejecta blankets are on that one. And I think Tycho is actually a pretty good example of all those very nice lines of ejecta that formed from all these secondary impacts around it. Yeah,
Very small impact craters we're talking about, are they all something that's happened in the past, or is that something ongoing? I missed that point.
yeah, so. Yes, they are ongoing. Yeah.
If so, how frequent is it raining?
It's not really rain, yeah, so I mean, we constrain times by taking images frequently of the same surface. And I think the narrowest we mapped was like few months. On Mars, it's much easier to constrain that because we don't have so many shadows. So images are all much better timed, but on the moon, it's sometimes harder, yeah.
So I have a question, just like any kind of analysis, as these models evolve, it's just a matter of should I say finessing these things and continuing to build on what someone else has done.
Yeah.
So is yours the first to actually include these other factors
Yes,
to do that?
Yeah,
Okay.
yeah.
How many other factors are there that could help make it, probably?
yeah, so one of the big ones is, well, actually, I was on a good one, okay. So here, I was showing how, I mean, now with the light, we don't see it, but here, we get the faulting, right? But we get, you can see it much better here, right? And so, however, so we can produce that now, but what we are not producing is what I mentioned, like the movement along these faults will produce additional heating and will produce additional vibrations. And if we are able to kind of account for the amount of heating along these faults and for amount of vibrations, we will be actually able to understand the hydrothermal processes that happen along these faults on other bodies, so not the moon.
Well, how much variation in heating is it compared to the actual median temperature that you would find? I'm sure it's not insulated because there's no atmosphere.
Yeah.
We cool up pretty quickly.
Yeah, so, and that's why I said, like, this is important it's important to understand it on the moon because moon does not have other processes, so we can actually observe craters that happened millions of years ago as they form now, right? Like, they are not eroded, nothing happened to them. But in terms of like heating and hydrothermal activity, that is something that is important for other bodies like Earth or Mars or places where we can retain that heat longer rather than on airless body where we lose it very quickly.
Any other questions? Thank you, Dr. Andrea.
Thank you.